and are required to divide the vertices of the graph into two complementary sets. The objective is to find the maximum number of edges cut. Note that this is equivalent to finding a grouping configuration such that the maximum number of edges is cut by the line separating the two sets. There is also a weighted variant of dispersion in which all edges are assigned a weight value. The objective becomes to find the maximum sum of weights of cut edges. You can also consider the previous unweighted variant as all edges having a weight value of 1.
Max cut in itself has various applications. One of them is for graph attack, which means that you want to know how to cause the most amount of destruction effectively on a given graph. And similarly, we can also use max cut to find out how to defend a network most efficiently. Also, it is interesting because it is a NP hard problem, which means that it cannot be solved in polynomial time using classical algorithms. And you may ask what time complexity means. Time complexity actually means that for any given algorithm, there is a certain rate that how the number of operation needs to when the number of input grows. And for the max cut, the time complexity is 2 to the power of n, where n here is the number of vertices. And as mentioned in the previous slide, we can use classical brute-force algorithm to test all the possible cuts, and it will take exponential time. So when the number of vertices grows, the time complexity will grow very fast, and it will take a lot of time to compute. However, it can be solved by quantum computers using QAOA efficiently, which means that it can be solved by quantum approximation optimization algorithm.
Now, first of all, a computer cannot understand a graph, so we need to transform the graph into something called a weight matrix or adjacency matrix so that the computer can work on the number. So you can visualize each number of the matrix is vertices of ABCD. So for example, here we have a value of 1, which is connecting B and A, so that we know that in the graph, the edge connecting between A and B has a weight value of 1, so here is a 1. And also you will notice that the diagonal of this weight matrix is all 0. It is because that the vertices is not self-connected, so it has a value of 0. And next, given an input, which is a weighted graph, we want the computer to solve for an output, which is a combination, because as we have talked before, we split the vertices into 2 groups, so we can represent the vertices by 0 and 1. And you can see here, A and D has a value of 0. That means they're the same group, so they're labeled as white vertices, and B and C is another groups. And so the edge between 2 different group of vertices are cut. So here, 4 of these red edges are cut because they're connecting different groups of vertices. And then we can construct a cost function, which is the sum of all edges cut. And I will explain this expression in the next slide. And as you can see, only different the vertices in different group gives a value of 1, so that the weight is capped because the weight is times 1, and other thing is all 0. So this satisfies our objective, which is that the edge between 2 different group of vertices are cut. And so the cost function is basically the sum of all edges cut. And the next thing, we want, after we have this expression, we can expand and do some algebraic work, and we can obtain a expression like this, which is a quadratic function, but in matrix form. And since we have substituted this q as a negative weight, so originally we have a maximization problem of we maximize the cost function, but now here we want to, this problem is transformed into a minimization problem where the cube is the negative weight. So, and also because this is a quadratic function, so this, where is the name cubo come from? This is a quadratic unconstrained binary optimization. So it's the main quadratic thing come from here. And then from the cubo, we want to find a Hamiltonian that encodes the cost function c of x, so that if you find such a Hamiltonian, then we can find the ground state of the Hamiltonian in terms, so that in terms we can solve for the ground state of Hamiltonian then, and then we can solve for the problem because it is where the cost function is maximized, or in this case, because it's a cubo, so it's a minimization problem, and by some algebraic work, people do find a solution of the Hamiltonian in this form, and this is very important because after we have the Hamiltonian, we can use this to construct the quantum circuit gate.
Now, before we move on to the implementation of the Hamiltonian, we will first talk about what is QAOA. So, introduced by Fahy, Goldstern, and Gum in 2014, the quantum approximate optimization algorithm is an attempt to solve combinatorial problems. It is a variational algorithm that uses a unitary gate U characterized by sets of parameters beta and gamma to prepare a quantum state. And the goal of this algorithm is to find the optimal parameters beta sub opt and gamma sub opt such that the quantum state encodes the solution to the problem.
Okay, so in this diagram, you can see that QAOA is comprised of 3 sections, also mentioned by Group 5. So in this blue section, the quantum state is prepared by using Heidemann gates to prepare a maximally superposed state of the quantum state. And then we move on to the green state where we compute the expectation value of the quantum state, and that's actually the cost function of that particular configuration by using the mixer layers and the problem layer, which Isaac will elaborate on soon. And then we fed the expectation value to the classical optimizer, where new values of the beta and gamma, which are used in this expectation part, which is here, is constructed, and then it's fed into the quantum computer again. And this cycle is repeated until an optimal solution is found when the expectation value is like the highest or the lowest.
Okay, so after the quantum states are being prepared using the Heidemann gates here, we first have the mixer layer, which encodes the simpler mixed Hamiltonian HM here. And then we have the problem layer, which encodes the more complicated proper Hamiltonian HC. And to note that HC is also the cost function of the Maxwell problem that we have derived in previous slides. This process is repeated for p times, and finally we can do the measurements. So you may ask, what is the purpose of a mixer layer? Well, let's first talk about quantum annealing. The fundamental framework of quantum annealing comes from the adiabatic theorem, stating that the state of the Hamiltonian will always stay at the ground state as long as the evolution is slow enough. Just like the graph on the left side, if we bend the slope slowly into the shape of the right graph, the ball is always staying at the lowest point possible. As a result, we can obtain a very precise and consistent extrema of the Hamiltonian, and this shows why quantum annealing is such an essential part in QAOA. So now back to the mixer layer. The mixer layer allows the slow transformation of the problem layer. And since the mixer layer is basically made up of, the Hamiltonian of the mixer layer is basically just poly X gates, it ensures that the ground state can be easily found. So by transforming the problem layer, the mixer layer can be turned slowly into the more complicated version, which is basically just quantum annealing, since we are slowly transforming the mixer layer into another version. And this results in a more complicated and accurate and detailed result of the problem layer.
And in fact, we actually lack the initial set of beta and gamma. So how can we ever use those those parameters to accurately represent the cost function. And this is where the classical optimizer comes in. The classical optimizer is a machine learning algorithm that helps find the maxima of a known function, which in this case is the mapping between the cost function and the sets of beta and gamma. And by inputting the results of the quantum computer into the classical optimizer, the classical optimizer will give us the new set of gamma and beta, and by recursively doing this thing, and we can find the sets of gamma and beta that can accurately represent the cost function.
So now let's move on to the implementation of the algorithm. So this is the quantum circuit for the mixed layer and cost layer. So we can take a look. Okay, so let's look at an example, a weighted example actually. So this should you should have seen this earlier in the presentation. So you can see the expected result computed by the classical algorithm is 0, 1, 1, 0, where A and D are in the same group and B and C are in the other one. So as for the results given from the quantum computer, you can see that there are two peaks in the diagram here, and they represent the state vectors 0, 1, 1, 0 and 1, 0, 0, 1 respectively. So it should be noted that these two are practically equivalent, because the values in the state vector only determines which group they're in. So you can actually imagine a line crossing through, cutting through these four edges as a visualization. We also have an unweighted variant for a more complicated graph with 6 vertices. And after some computation from the classical algorithm, we can see that the state vector is 0, 1, 0, 1, 0, 1 for the maximum cut, which means that A, C, and A are in one group, and the rest are in the other group. You can also imagine this as a single line cutting through all of these edges, cutting through the red lines. And as for the results from a quantum computer, you can see that it is kind of difficult to see. So I printed out the two peaks with the state vector, also their value in the count. So you can see that they are 1, 0, 1, 0, 1, 0, and 0, 1, 0, 1, 0 respectively, which similarly are practically equivalent.
Testing. Okay. So now I'm going to introduce original problem as like a variant of the max cut problem, and you can think of it as like a harder problem to the traffic salesman problem. And this is what we call the traffic light problem. So in this problem, a person must travel from point A to point B through this traffic light lattices, and the lights change over time. So and our goal is to minimize. Is to find the optimum traffic light configuration that's like the red, green, such that the person can travel from point A to point B in the minimum time. Okay. So let's talk about the roots of this problem first. So in this problem, as I've mentioned before, the lights changes, they reverse the color in delta t. So in this specific example, delta t can be 2 seconds. The person can cross the road when the traffic light he's standing on is green. So like in here, in point A is green, so the person can cross to the next, can cross the road to point C. When time is equal to 2 seconds, which is not shown here somewhere here, the traffic light changes the color. So this point C changes from green to red, right? But by route 2, which we can just look. The person can still keep crossing the road, unlike in like real life situations. So the person comes to point C at when time is equal to 3 seconds, but he cannot cross to the next road like these two because C is red. So he has to wait for 1 more second when T is equal to 4. So then he can cross to another road. So because T is equal to 4. So that's like a multiple of delta t, right? So after some calculation and manipulation, we have arrived at this time cost function of one route in one configuration. So it's basically a summation of the crossing road time, which is this capital T, and it's like, and we need to add it with the waiting time, which is this part, because if we need to wait for the red light to change to green. And after some manipulation, we have also arrived at this simpler and general form of the type cost function. But unfortunately, as you can see from the size of the traffic light problem of the type cost function, it is very hard to derive the Hamiltonian from that, and it's also very hard to implement the functions in a quantum computer. Moreover, we need two optimizations for this problem, which is unlike the conventional QAOA problems like MaxCut, as we need to find the best path when we have one traffic light configuration. And then when we have the best path, we need to find the best configuration from that.
So in conclusion, MaxCut is a problem that can be solved efficiently with QAOA, and some other NP-hard problems like that, like as aforementioned, like the traveling salesman problem as well as the portfolio optimization problem. In QAOA, we employ a scheme similar to quantum annealing, where we to find the optimal parameters. And we have also come up with an original example where QA can possibly be used, but its Hamiltonian is rather difficult to compute. So there's also a simple derivation of the cost Hamiltonian from our previous slide. So, and with that out of the way, this is the end of our presentation, and we thank you for your attention.
Okay, thank you for your presentation, and we have a question for you. Now, in your calculation, how many beta and gamma are you using? And what happens if we increase the number of parameters?
Oh, we use 2p. So in theory, we can use 2p of gamma and beta, so that we use p values, we use p beta and we use p gamma, but in our case, for simplicity, we just use 1p, I think. So we use...
Yes, we use a set of gamma beta because the simulator, have limited capacity. But in a general QAOA, we can take as many as layers of gamma and beta, and also the accuracy of this algorithm. This algorithm will be more accurate if we increase the number of layers infinitely. Yeah, in theoretically.
But also be aware that there is some error, so we have to balance between the number of parameters and the number of errors that will accumulate. So I remember that by some paper, that's the number of vertice size grows. The most optimal number of parameters is a linear relationship between the number of input and number of gamma and beta.